Sea level rise is one of the most urgent consequences of climate change, and in the Delaware Estuary, it creates a hidden but serious risk, saltwater intrusion. Today, I'll be talking about how rising seas allow ocean saltwater to creep further inland, threatening Philadelphia's drinking water supply. Roughly 60% of Philadelphia's drinking water comes from the Delaware, so even small changes in sea level can have major impacts on health, infrastructure, and resilience. As sea levels rise, estuaries like the Delaware face unique challenges because they are transition zones between freshwater and saltwater. These systems are extremely sensitive to even minor shifts in sea level because they depend on a balance between freshwater flow and ocean tides. Rising seas occur through two main processes, melting ice and thermal expansion of seawater as it warms. Both processes increase overall water levels, gradually elevating the baseline sea level, which allows saltwater to move further inland and alter salinity. In a funnel-shaped estuary like the Delaware, this natural geometry amplifies tidal influence and saltwater intrusion. Essentially, the narrowing of the river channel pushes the saltwater upstream more efficiently, forming what's known as a salt wedge. This is represented in the diagram to the right, where the denser saltwater from the ocean undercuts the lighter freshwater flowing downstream. Factors such as storms, tides, and drought conditions can further intensify this intrusion by reducing freshwater flow and allowing saltwater to dominate temporarily. On the left, the video of the water surface elevation data illustrates this, showing how tides and sea level variability affect the Delaware Estuary's water surface height over time, making it a hotspot for salinity changes. Together, these processes explain why estuaries are vulnerable to sea level rise and why understanding these physical dynamics is essential for managing freshwater resources. The Delaware Estuary is a critical ecological and economic hub, supporting over 15 million people across 4 states. Philadelphia's vulnerability stems directly from its geography and dependence on the Delaware River for drinking water. The city's Baxter Water Treatment Plant, shown on the map here, draws water from the estuary just upstream of the average salt front location. Under normal flow conditions, the salt front stays far downstream, but during droughts or low flow periods, it can migrate closer to Baxter's intake. This makes Philadelphia's water supply particularly sensitive to both sea level rise and seasonal variability. The lower chart on this slide shows tide predictions for the Delaware Estuary. These tidal fluctuations highlight just how dynamic this system is. Water levels rise and fall daily, influencing how far saltwater can penetrate inland with each tide. These constant shifts mean that even the smallest increases in baseline sea level can have large consequences for both human and natural systems in the region. Philadelphia's location at the upper end of a tidal estuary places it at the front line of climate-driven sea level change, where natural variation and long-term rise increase risk for millions. Historically, saltwater intrusion has already posed significant challenges during drought events. During the 1960s drought, the salt front advanced dangerously close, within just 8 miles of Philadelphia's intakes. This is the furthest on record. More recently, the 2024 drought, the Delaware River Basin Commission recorded salt front positions as far upstream as 18 to 23 miles. Normally, the salt front sits around 35 miles away, but its position fluctuates significantly. The box plot graph on this slide, based on DRBC data, illustrates the variability in salt front locations across different flow conditions. Even in recent years, a clear trend toward higher variability and further upstream movement during dry periods is evident. Future projections are even more concerning. With continued sea level rise, the average position of the salt front could reach the Baxter plant intake by around 2100, particularly under high emission or low flow scenarios. Beyond a gradual rise, storm surges can cause abrupt temporary saltwater pulses that travel rapidly upstream, sometimes within hours. These events demonstrate how the combination of drought, storms, and sea level rise can increase both the frequency and severity of saltwater intrusion threats. So what's at stake? The implications of saltwater intrusion extend across multiple sectors. First, water supply. As saltwater moves inland, treatment plants face higher salinity and potential contamination risks. This can increase treatment costs and, in severe cases, limit available fresh water for distribution. Second, infrastructure. Increased salinity and acidity accelerate corrosion in pipelines, pumps, and storage systems, driving up maintenance and replacement costs for municipal infrastructure. Third, ecosystems. Salt intrusion alters habitat conditions for many species. Wetlands and tidal marshes may experience dieback, while fish and shellfish populations face stress from changing salinity levels. At the top of this slide, the NOAA dataset shows a steady long-term rise in sea level along the Delaware Estuary. This upward trend provides clear evidence of how baseline water levels have increased over time, setting the stage for more frequent and intense saltwater intrusion events. Below that, the map projects how salinity distributions are expected to change under future climate conditions. The orange and red areas, representing higher salinity, extend significantly further upstream by the end of the century. Together, these visuals demonstrate how rising sea levels and changing hydrology are reshaping the Delaware Estuary, emphasizing the urgent need for adaptation to protect water resources and ecosystems. Protecting Philadelphia's water supply will require a combination of engineering, policy, and community action. From an engineering perspective, potential solutions include estuary barriers, desalination systems, and reservoir releases that help dilute saline water during drought periods. These are represented in the schematics on the right, showing different barrier and water management options. Policy solutions involve stronger monitoring, regional drought planning, and long-term investment in climate resilience infrastructure. At the community level, water conservation, public awareness, and climate action all play crucial roles in reducing stress on the river system. Protecting Philadelphia's water requires all three: science, policy, and people working together. Protecting Philadelphia's drinking water is a local expression of a global issue: rising seas driven by climate change. Global change has local consequences, and acting now is essential to ensure safe and sustainable water for future generations.